You can take something out?
Oh, my notes and stuff, my homework.
All right. Okay, so anybody have any questions from yesterday?
You go over the hidden metal, like 16 one.
Yeah. Okay. So, if you look at what's happening on 16, right? So, you've got L equals L naught, 1 plus alpha delta T. So here's the whole key to this. Keep in mind this is not the temperature of the system. This is the change in the temperature of the system. So listen to me very carefully. This is the change in temperature of the system. So basically it's an algebra problem. So you're told that it's 0.5, so there's your L naught, okay? And then you got 0.50068, so there's L, and you've got the raised by 80 degrees Celsius, so you've got that. So it's just a matter of isolating this value of alpha. So personally, I would divide by L naught, and then have 1 plus alpha delta T, and then maybe subtract 1 over or something like that, and then divide by that delta T. Now here's what you have to be careful of though. On that data sheet, these are all listed as exponents of 10 to the negative 6th, so you just have to be careful where you put that decimal point because it's 10 to the negative 6th. So it should be a pretty small number. So it's just an algebra problem at that point. Okay? Now, let's talk a little bit about on question number 7 and then question number 8. So there's a couple of different ways you can do that problem depending upon your preference. So one thing that you could do on number 7, that's just kind of a smash mouth approach. You've got PV equals nRT. Boom, here you go. Now, so your answer to number 7 should start with a 2 and be something times 10 to the negative 3rd. Okay? In cubic meters. So on number 8, if you look what's happening on number 8, it says what's going to be the volume if the pressure was doubled and everything else was held constant. So you kind of have to visualize how we measure pressure. So let's say that this is my pressure sensor. Okay, so let's say this whole big board is my pressure sensor. So basically what we figured out is a way to take the pressure created by little bits of matter, nitrogen, oxygen, okay, hitting this pressure sensor. And then that's going to transfer to a number that we've arbitrarily chosen. So even if you look at what happens when you check your pressure on your tires, okay, so when you put that air chuck over that, and it's going to go out, it's going to read a certain number, maybe like 35 psi. So what happens is that within this system, you have all these little billions upon billions of little particles, and as soon as you give them a way out, they come out, boom, here you go. So there's 2 alternatives you can do to raise the pressure. So one option is that you just have more collisions, okay? So you can either increase the number of particles or you can shrink the room. So imagine that you have a room full of second graders, okay, and it's a fairly small room. And here's our pressure sensor. So we're going to keep track of how many little Timmies run into the wall in this area. We're going to say, okay, hey, this is Timmies per square meter or whatever it is. So imagine that we're going to keep the same number of Timmies, but then we're going to shrink down the room. Okay, so if we shrink down the room, what's going to happen to the number of collisions with the board? It's going to increase. Okay, so that's one option. To increase the number of collisions, you just make the volume bigger because the particle is going to be more likely to collide with this. Now the other option is that, when this thing is hit, right, that's going to create a certain amount of pressure because I'm just kind of tossing the golf ball at him. Now imagine I give this Shively, and Shively rears back and he throws the golf ball as fast as he can. Okay? So if he throws it as fast as he can, he's going to increase the kinetic energy of the particle. That's like raising the temperature. So as you raise the temperature, these particles are going to hit, not necessarily with more collisions, but certainly with more kinetic energy. So if they hit with more kinetic energy, that's also going to see an increase in pressure. So and you can actually combine both. So if you shrink the room and increase the kinetic energy, then you're going to get a really big increase in pressure because you have both of those things happening. So you're shrinking the room and you're giving all the Timmy's bags of Skittles, hello, that's going to that's going to increase that pressure a lot, okay? So that's one way that you can kind of conceptualize it. So when you get to actually doing number 8, so one option is that you can do smash mouth physics. So you can come in here and say, okay, I got PV equals nRT. You found the volume on number 7 with a certain pressure, a certain number of moles, a certain R, and a certain temperature. So basically what we're saying is that we're going to increase this pressure. So if you're going to double that pressure, okay, then you could go back in and recalculate everything. So you could take the pressure from number 7, plug that in, and recalculate the whole thing, and you can find that new volume. Okay, that's cool. If you like smash mouth physics, that's the way to do it. There's a slightly more elegant way to do it. You can sit here and go, well, if nRT stays the same, and this is P1, V1, and then that has to equal P2, V2. Okay, so because the N and the R and the T are all staying the same in this situation. So then you can just go, oh, that's P1, V1 equals P2, V2. So you know these two, you know the initial pressure and the initial volume. Plug in the new pressure, figure out what the new volume is. Okay, that's an option. Or you could go on you can almost solve every ideal gas law equation by going P1, V1 over T1 equals P2, V2 over T2. So in this situation, when we're keeping everything the same, you can start with this, go, oh, temperatures are going to stay the same. I don't have to worry about that part. So that's just P1, V1 equals P2, V2. Hey, we're off to the races. Okay? So I don't care how you think it through, but that's kind of what you need to be able to look at. On number 13, keep in mind that I'm asking for the change in area, and I don't care if you work in square centimeters or if you work in square meters. I don't care. Okay, I don't care. I just need to know which one that you chose. But no matter what, your answer to number 13, because it's asking for the change, should start with a 1, and your answer to number 14 should start with a 3. It's just a matter of where you put the decimal place. Okay. Make sure on number 11 that there's 2 parts to that answer. I want to know what's the final length, and then how much will the length of the change in centimeters. So those are the 2 parts that you need. Okay? Cool with this. Now, so on first block, it was an interesting discussion. So if number 18, it's like, why do you have to have expansion joints? And Nick Reiswick asked, like, well, how do you physically build the expansion joint? So if you look at what happens with bridges, if you drive underneath one or whatever, typically what you'll see is you'll have them in sections like this, and then in between there's got like a hard plastic buffer that kind of fits together like knuckles like this, so they interlock. So that way, as the bridge expands and contracts, it can slide past each other, but yet you have a small enough gap that people can drive over it without any problems. So this is why you don't pour these bridges in one big section. This is why you break them up and you give them these expansion joints where they can move and flex. So the other classic story about this, there's 2 classic stories about expansion. So if you've ever been to the Cosmosphere, okay, when you walk into the Cosmosphere, there's the SR-71 Blackbird, okay, hanging up there. So if you've never seen it, it's like this jet spy plane that looks like this, and right, and it would fly like at Mach 4 or something like that. So when it would fly, it was going so fast, and even though it was flying like at 30, 40,000 feet, it would still be flying so fast that the surfaces would get really, really, really hot because of the friction. So this metal that they built it out of had to be able to expand. So when the plane was on the ground, like at room temperature, even the fuel cells were built with a gap. So when the plane was sitting on the tarmac ready to take off, you would actually see fuel dripping out of the plane. because of the fact that they had to leave gaps in the fuel tanks so that when they got up to temperature, then the fuel tanks then would close up and they would seal up and then it wouldn't leak. But you had to leave that gap, because if you didn't, if they were already sealed, if they were already sealed up, then when they expanded, then the surfaces would do this. So they had to leave enough room for it to expand when it got up to temperature, that then it would seal itself up. So they actually had to develop a special fuel just for this plane that was very, very, very low volatility. So because they knew it was going to be leaking out on the tarmac, so they went to, I don't know which one of the refining companies and said, hey, here's what we need. We need a brand new jet fuel. And it was cool because you could actually take like a cigarette and flick it onto that fuel that was dripping out of the plane, and it wouldn't ignite because it had such a low flash point. But within the engines it would burn, but it wouldn't burn if it was just out here on the ground. So, and the whole plane was built that way. So if you look at that plane, there's gaps in the metal, because that way when it would heat up at temperature, those gaps would close because that metal would expand. Now, the other cool thing on how this works, if you've ever been to St. Louis and seen like the Gateway Arch, okay, you know what I'm talking about? That big impressive arch. So when they built that, they actually built it from each side coming up like this, okay? It's made out of metal, and it was a great engineering feat. And so when they went to put in the last keystone piece up here at the top, initially it was a cloudy day, and they had machined this piece to just fit within this gap. So they got the crane, they lifted it all up, they're getting ready to set it in there, and the sun came out. The sun came out and it heated up the arch. And because it was such a vast length, when that sun came out and it heated it up, it closed the gap on the top of the arch where this metal piece wouldn't fit in. The sun came out. They were trying to do it on a cloudy day, and they thought, so that what they had to do then is they had to get fire trucks, and the fire trucks are spraying water on both sides of the arc to cool it down so that that metal would contract so they could wedge that piece of metal up there into that center part, because they had it constructed with such small tolerances that being heated by the sun expanded that metal to the point where it wouldn't fit. So anyway, so there's your bits of expanding metal trivia that ever comes up. Okay, anything else on the assignment? Going once, going twice, what?
I'm confused on 15.
On what?
15, the one with aluminum and copper, which one is going to code?
Okay, so here's aluminum, right? Here's copper. What's the expansion rate for aluminum?
24 times 10 to the
Okay, what's the expansion rate for copper?
17 times 10.
Okay, so they're both 10 to the negative 6, right? So if I heat this up, which one's going to expand more, the aluminum or the copper? Aluminum. So for each temperature change, the aluminum is going to try to expand more. So this is, as that expands and that copper is expanding less, it's going to force that down towards the copper because your aluminum is expanding at a greater rate. Okay?
Thanks.
Now, one of the things that we got very lucky on as a species is your answer to, on 12, iron is used to reinforce concrete. So one of the great things that we got very, very lucky on, and it isn't like we had this planned, but concrete and iron expand at the same rate based upon thermal changes. Because if that wasn't the case, like if iron didn't expand at the same rate, or copper or the concrete didn't expand, we couldn't use metal to reinforce concrete. Which, if you've ever seen concrete being formed, okay, you lay like this mesh or you lay rebar. I mean, it's used all the time. So if that was the case, if they didn't have the same expansion rate, then you couldn't do it. I mean, either the metal would always break free of the concrete because the metal was expanding more, or if the concrete had a bigger expansion rate than the iron, then that metal would be pulling itself away because it would be expanding more. So one of the things that we got very, very lucky on is the fact that concrete and iron have the same expansion rates. If they didn't, we couldn't use concrete the way we did. So we'd like to say we had that plan, but we didn't. It just worked out that way. Okay, anything else? Once, twice sold. All right, there's another ping pong ball that I'm going to roll down this end, and it's really tight fit around. It just barely fits inside of here, and it's kind of cool when it rolls. So listen to the sound. Okay. So pick that up.
Is that PVC?
Yeah.
Yeah.
It's a PVC pipe. So what I'm going to do
Oh,
then
it's the rubber.
is that I got a piece of Mylar. This is like an emergency safety blanket. And I'll put this over this end and put that coupler on there. So I got that end sealed up. And we'll put the sacrificial can right there. And then I'm going to take the other end and put it on here. Okay? So right now, what do you think the pressure difference is between the inside of the PVC pipe and the outside?
Probably isn't one.
Yeah, the same pressure, right? So within the PVC pipe and outside, and hitting all of us, there are billions upon billions upon billions of these tiny little particles that we've already called molecules, nitrogen and oxygen, because they're diatomic, and they're bouncing around of us and they're creating this pressure, and we just take it for granted that it's here. So what I'm going to do is I'm going to take a vacuum pump and I'm going to remove all of the nitrogen and oxygen molecules that are inside the tube, okay? And that's going to create a pressure differential. So I'm going to do this, and as soon as I do that, you'll see that the ends are automatically get pushed in, okay? So it's like this concave surface that are perfectly symmetrical. Good?
Yep.
So here's the question. What's happening to make that surface look like that?
The molecules on the outside are hitting it in.
Yeah, you still have the same number of particles pushing on the outside, but you don't have the same number of particles pushing on the inside, so therefore you have a pressure differential. So what I'm going to do is I'm going to puncture this in. Now, move. So if you're sensitive to loud noises, you might want to cover up your ears.
Here we go.
Okay?
That was really loud, actually.
Told you.
I know, like that one.
God.
Pipe down, pipe down.
I was not expecting that loud of
I saw a duck pop.
What?
Pipe.
I wasn't expecting
I
that loud.
told you it was going to be.
That was crazy.
That was cool. Do it again.
Yeah, can you do that again?
I closed my eyes and you did it again.
Okay.
Maybe we should shoot the line this way. Yeah, what's that?
Okay. So, what happened?
All the pressure, all the air went in there
Okay.
and shot out the other side.
Was work done on the ping pong ball?
Yes.
Absolutely, right? So this is roughly about 1 square inch down here. And right now, there's equivalent of 14.7 pounds per square inch. So there's like a weight of Hank the bowling ball that was pushing in on this end. So here's the cool thing is that if you look at this and you go, oh, okay, right. So that got punctured. As soon as that got punctured, billions upon billions upon billions of little nitrogen and oxygen molecules that we can't see came rushing in to fill that void. So they were rushing in there so fast that they carried that ping pong ball with it and then blew out that Mylar on the end. Okay? What?
It was awesome.
What
And
else?
Hunter wants to stand at the end of it to play some sting pong.
Oh, dude, I played
no.
some gnarly sting pong. My back was, I had a picture, it was like middle school, my back was so bad.
Really?
Yeah.
That's the first time that's ever happened. A guy did something stupid in middle school. That's
story.
never happened before.
Can Hunter do something stupid in
the
high
myth,
school?
the legend.
No, because I'd done that stupid thing on a dare.
Did it hurt?
At the time, the superintendent at the time was a buddy of mine from high school, I knew, and Doug Powers. And I was showing him, and he happened to be walking through. He goes, "Hey, take one." And the guy was like, "Okay, don't." I had a welt for like 3 weeks.
I already have hickeys on my back.
Huh?
What?
It's cupping. You know what that is? I've had them like 3 weeks already.
Okay.
Yeah. I realized that. Right as I left, I was like, ooh, probably should have said the cupping on my back.
All right. So Now, I don't, because this works on a very, very critical vacuum, so we'll try it again. So, a lot of times that vacuum pump has to like cool down in between. We'll try it. If it doesn't work this time, we'll revisit this again at the end of the class. So we'll try it. I make no guarantees on this one. So,
Put a 1 kilogram mass in there.
Do you want to go stand in front of it?
So is this where we put Eli in front of it, since there's no guarantee that it'll shoot?
Since there's no guarantee, can we put like a 20-gram mass in there?
That would be the nasty.
You can find the force of the pressure. Okay, now
Let's put a bullet in there.
so
Thumbtacks.
Shotgun shell.
I just got to show them how that would work.
After the shotgun shell, just tear apart the PVC. It'd probably hit.
Can you show his mom?
She was so mad, and you be.
She's like, you had such a cute butt.
So wait, is the kinetic energy of the ball equal to the energy of the molecules?
The ones that hit it, yeah. But, well, probably not their total energy before, because they didn't stop dead. It's like, stop.
They deserve some entertainment too.
They get plenty of
Record it.
entertainment. I
Someone
filmed
record
the
it.
entire
Slow-mo.
class.
Times like these. Times like these, Barry. I'm always prepared for the
What's he doing? Yeah.
You
Punish.
said record it.
yeah, but imply your phone was over there and you're gonna get it.
No, he always has.
Just always right.
Oh, way to snitch out, Felix.
Get the diss up.
I do it for this. I do it for science.
Like, it's okay. It's okay.
It's all for science, Bird.
You already have your iPad, so I
So,
Like a slow-mo shot.
So we'll try this. I don't know if it'll work. We might have to let that pump cool down and go back.
Mr. Burkamp,
I don't make any
Don't.
guarantees on
We'll
this.
figure it out later.
the energy?
He'll explain it in a lecture, probably.
Are the things getting
Tell me
If
when to start
not, you can
recording.
just ask later, because he'll probably explain it later.
Why are your fingers so long? Your fingers
Are you
look,
gonna cover your ears?
No.
your fingers look really long. Like, I don't know.
Which is probably going to make me jump, and then
They
this.
look short otherwise?
No, they look, I don't know.
It's got some fish in it.
Don't worry, I'm a scientist here.
Oh wait, can you put the pencil? Can you put the pencil next to your finger? I want to see like a comparison between your pointer finger and the
No,
pen.
like,
No,
your
like
finger
just stick out your
straight.
pen.
No, like-
Just stick out your fingers straight. Huge fingers.
Okay, make no guarantees on this one, but we'll try.
Did you say that man's built
Okay.
like an array?
Here we go.
3, 2, 1.
Louder.
I got too scared.
So let's check this.
I think Nick was about to say it's even louder in person. You're the only one who's like actually being safe right now.
You're right. I like my eyes.
Oh, just see if I can see this on there.
Oh, ready? So you can see this? Let me know if you can see it.
No, stop.
Let me see it.
None.
Okay. No, we need to stay right here.
We do more experiments?
Let's just.
Like, wow. Okay,
It was so slowly.
all right.
Oh, awesome.
So what we're gonna do is we've got this little plunger here.
That's where they were.
He had to make a decision.
No, if I
If he loses an eye, it's his fault.
Chauncey deceleration kinship.
So,
It's like a wall.
so this just slides up over this, okay? That's just,
This MX still has to stay up in the.
all right. So I'm gonna take this, give this a
guys
push
planning my
down,
death?
and I let go of it, okay? Comes back up, right?
Oh.
So, by the definition of magic, that's magic.
Yes. Yeah.
Because I let go of it and it moves on its own.
It's like beginning magic. You
It is
know?
beginning magic.
beginner.
I didn't say it was advanced, okay? It isn't like I'm going to lift this up and like a rabbit appears, okay?
Yeah.
It's no
No,
necromancy.
it's really not my style. Okay, that's like biology. Really not my
I love necromancy.
Okay, so if I push this down slowly, what's happening to the pressure inside that container.
It's increasing
Why?
because the volume is decreasing with the same amount of things.
Okay,
the
no,
temperature.
just don't tell me because the volume decreases. Physically, what's happening?
There's the same
Particles
amount of
start to
particles in
fly
there, the same
more,
temperatures. There's multiple.
Now, particles are actually a little bit claustrophobic, and they tend to overheat when you get them really, really close to each other. So, as I compress this down, am I doing work?
Yes.
Okay, I'm exerting a force over a distance, true? Now, when I let go of it, is the gas doing work?
Yeah.
Why? Yeah, it's forcing the cylinder back up. So, if you think about it, the gas actually has to do a lot because I've got it easy because I'm pushing it in the direction of gravity. So gravity is actually helping me out, right? When I let go of it, it's got to overcome the gravitational pull that's trying to pull this thing down and force it back up. So here's what's important. Gas particles can do work. They can exert a force over a distance. So when I push this down, boom, let go of it, comes back up. So the other thing that's going to happen is that I'm going to increase the internal energy of this system. So if I do this very slowly, I'm allowing that a little bit of that energy to flow out. So what I'm going to do is I'm going to do the same thing, but I'm going to do it very, very quickly. Okay? So what you want to watch is that little bit of cotton down there at the bottom. Okay? Hold on. Sometimes it. Reverse vaping.
Yeah, you did blow up loud.
Does it work like a charm first block? Okay. Okay? A little bit of fire, right?
It caught fire.
Okay?
Wait, I blinked.
Okay, we're doing it again. Okay.
I don't think
Wait.
I can not blink.
What a blow dart gun. Okay?
I bought one of those last weekend.
Did you really?
My little brother, yeah.
Acapellas?
no.
Yeah.
Can you,
It's
how
like
much are
$12.
they? I kind of
Like
want
$12.
Really?
Did you get a?
Does it
Blow
come
dart
with,
gun?
does
Did
it
you
come
get
with
a-
like poison tips?
No, they're just like.
Oh,
darn, where's the fun in
You can put like Tic Tacs in there, or not Tic Tacs, tags.
Get paintballs though. They have paintballs for blow guns.
Okay.
Those
So,
would probably hurt too.
okay. Don't blink.
I'm gonna really try not to. I don't
Okay,
think I
if
can.
you want to record it with your phone,
Give me if you blink.
Do we need it?
if you want to,
All right, Olivia.
Okay, wait, what?
so record it
Okay, yeah,
on,
record.
with the high speed,
Yeah.
and as soon as you get done, the phone's going back over there on the wall. Okay? Right? Okay, you ready?
Yep.
Hold on.
Disappointment.
Back
Waste of
off me.
storage right there.
My God.
Waste of storage, yeah, he's only got a certain amount of gigs.
Cool days.
What?
It smells like burning.
It smells like there might be a fire burning man right now.
Okay, let's try
Is
it.
bird spitting fire?
Ready?
Yeah.
Do you see it?
No, gonna be honest.
Oh.
I can't not blink because it's so loud, and then I'm like,
It's not loud!
it's kind of loud. I don't know.
So what we'll
Okay.
do, have her close her eyes, we'll tell her to open, then you do it.
Yeah, it's like taking a picture. Oh, now I saw it.
Okay, good.
Okay, now I'm good.
Okay. Now, so here's the question. When I do that slowly, nothing happens. But when I do it very rapidly, it does. What's the difference?
The energy can leave when it's going slow.
It can't leak
You're
out.
not
It's a lot
giving
more
energy
Yeah,
time to leave.
when I do it slowly, it's like trying to light a match. If I strike the match slowly, I'm giving that energy time to escape out, and the light doesn't match. If I light the match doesn't light. You know what I meant. But if I do it very quickly, then it ignites. So the same thing is happening here. So if you're all familiar with diesel engines, okay? Diesel engines don't have spark plugs. Diesel engines work by a compression just like this. So they have very, very tight tolerances, and they have a very, very rapid compression. So when you compress that diesel fuel and gas mixture, it ignites and pushes that cylinder back down. Now, if you have a gasoline engine, what ignites the fuel?
Spark plugs.
The spark plugs do, okay? The spark plugs throw that ignition source in there. You still compress it, but then that ignition pushes it back down. So here's the cool thing about this, is that if you look at this, okay, if you just saw this, okay, with those burnt ends on it, and there's black on it. You would think, wow, you held this near a flame and you singed the edges of this piece of cotton. So there was no accelerant. I didn't add gasoline, anything to it. So the same oxygen and nitrogen molecules that you're breathing right now, if you compress them, you increase that energy so much that you can use it as an ignition source. Okay? So, but it has to happen very rapidly. So here's what you have to understand. When particles get compacted like that, very, very rapidly, they don't like it. They flip out, okay? And they've got all this energy, they're going, ah, right? And they're like a thermal scream. And so then what's happening is that they have so much energy that they interact with that cotton that they cause that cotton to ignite. And if it's a diesel engine, it causes that diesel fuel to explode, okay? So when you compress gases, you do work on it, and you increase that potential energy, or the kinetic energy. Got it? Good? Grand? Back we go.
So if you could put the whole like swirl.
Oh, yeah, basically, yeah.
So that's funny. Huh, it's funny, I still don't see a blue phone up there.
What, you need it?
I put it up there.
No.
Where is it? I don't see a bright
Where is
blue
it?
phone up there.
Top left.
Oh, yeah.
Oh, there's nothing in there. You just slide right to everyone's faces. Huh, I hope you feel okay. Alright, you're all hypocrites.
What do you mean?
There's one person in this room other than me, guaranteed. Who?
Who is it?
So the phone's still not up there. Sorry. It's not popcorn.
Okay.
Nick, go on. Go on.
Come on. Yeah, we'll wait for it.
Yeah.
What?
Yeah, we're hypocrites. We're hypocrites.
Just so they can see your shame.
With that pipe one, it's like, is it like thunder? Like, cause like, there's a small volume and then you pop it and then big noise and then all that.
To a certain extent it is.
Okay.
Because what makes the noise is that once those gases hit the end of that, you have a rapid expansion. So that's what's making that noise. And hitting the can and everything else.
Alright.
Okay.
He still didn't put his phone up, and he called us all hypocrites.
I literally just put it up.
Where is it?
It's right next to my
Are you
phone.
kidding me? I made sure everyone saw it. I was like this. I was like, and I dropped it in.
I believe that he did.
Yeah.
So we're good.
No trust.
Okay. So what I did, wait, no, hold on. Wait, no, I don't. So all this is a cup of hot water, okay? We can verify that it's just really hot water, okay? And this is what's known as a Stirling engine. And so what I want to do is I remember which way this thing spins. Go this way, okay? So I'm going to give this a turn, and what's happening is that it's taking in this thermal energy from the cup. So first off, let's talk about microwaves. How do microwave ovens work?
Radiation excites the water.
Now they actually don't do waves.
They excite the water molecules in the pool.
Well, no, they do, but that's like step 2. So how are microwaves carried? What do you call a bundle of energy that is emitted from an atom?
A photon.
A photon, right? You all are being bombarded with billions of them right now. Okay?
Feel it.
So what they figured out is that microwaves emit a certain wavelength and frequency of photons. And so water molecules have what's called a resonant frequency. So what they figured out is that microwaves hit the water molecules with that right amount of energy. And then those water molecules begin to vibrate. As they vibrate, they have kinetic energy, voila, things heat up. So what I did is I took this cup, stuck it inside the microwave for a couple minutes, and a whole bunch of photons interacted with a whole bunch of water molecules, and those water molecules begin to vibrate. So what's happening here is that that air right above the surface of that cup is very, very warm. So within this area down here, there's a diaphragm that's moving up and down. So basically what it's doing is that it's drawing this warm energy in that has a lot of kinetic energy, just similar to what I did by compressing it. So warm molecules, nitrogen and oxygen, have kinetic energy. So basically what's happening is that this thing is drawing in that energy. It's using part of it to spin the propeller, and then it's expelling the rest of it out into the environment. So this is only going to, when you notice it's going to spin faster and faster and faster. So once you kind of get that system warmed up, then it will just go and go and go. And it's called a Stirling engine. So now, if you like run out of gas, you know, in your car, and go, oh, I still need to get to town. Great, I'll make a pot of coffee and I'll run my engine on some hot water. No, won't work. But it does work with a simple motor. Okay, you couldn't do any real heavy lifting with this. But this idea is basically how all engines work. Is that you take in some type of thermal energy, you use some of it to do work, and then the rest of it gets kicked out, which is why your car has an exhaust pipe. Okay, because it's kicking out that excess thermal energy out that you're not using. So cars, for example, are typically, and human beings are also about 25% efficient. So when you buy, 100 units of energy for your car at the gas pump, you're only going to be able to use about 25 of those in terms of like functional things. So the same thing is true. If you consume 100 calories of food, you're actually going to be able to only use about 25 of them to do work, to write whatever. Because the other 75%, a lot of that's just going to be wasted on thermal energy, which is why people give off heat, because of the fact that on a cellular level, you've got a whole bunch of tiny little engines that are doing work, and they're giving off energy as a byproduct through that process. So this will work, this will run, I don't know, probably 10, 15 minutes, as long as you've got enough warm air in there. If you were to continuously like warm up the cup, that thing would just keep going and going and going, and basically until it runs out of fuel. Okay, so when you look at thermodynamic calculations, so you need this sheet of paper with all of the constants on it. Okay? So and for those of you that were in Chem 1, you might have seen this equation. Q equals M, delta T, C sub D. So all these equations that we're going to be dealing with the thermodynamic side are on the back side of your equation sheet. Okay, so you're going to have these. You're going to see that we're going to have 3 different calculations for Q based upon the situation. So let's talk about what Q is. So Q is the measure of energy in the system, and that's going to be measured in joules. So here's the classic differentiation between like temperature and heat. So you can light a match and burn your fingers, but it's not going to warm up the room. So by lighting that match, those particles that are coming off that match have a tremendously high temperature because they have a lot of kinetic energy. But you're not going to warm up a room because you don't have very many of them. So this calculation of Q is the sum total of all of the energy that's going to be in the system. Now, there's a couple of things that are going to be important. The first is this concept that this only works on a change in temperature. So when I took that coffee cup and I put it in the microwave, that water was at a certain temperature. So I want to raise that temperature up. So what that Q is going to tell me is how much energy that I had to put into that cup of water to raise the temperature a certain amount. Now, you'll notice that all 3 things are multiplied together. Mass, change in temperature, specific heat. We'll deal with specific heat in just a second. So this should intuitively make sense. So if I want to heat up a cup of water versus 5 gallons of water, what's going to take more energy?
5 gallons.
5 gallons. So the more mass that you have, wow, the more energy that's going to take. the change in temperature. The bigger the change in temperature is, the more energy it's going to take. So if I want to keep that water from 20 to 25 degrees, hey, that's not a big change. That's not a big deal. That's not a lot of energy. But if I want to change it from 20 to 90 degrees, that's going to take a lot more energy. Now, so here's the deal with energy. Energy flows two ways. Everybody's used to thinking of energy being put into the system, and that's what we do a lot. But that Stirling engine actually works in the opposite direction. That water is actually radiating thermal energy out. So not only can you calculate the energy that goes in to warm something up, you can also calculate the energy that is given off when that system cools back down. Okay, so there's two ways to view this thermodynamic calculation. Now, let's talk about specific heat. So if you look on this sheet O paper, okay, up here at the top you have a list of, which is in no way a comprehensive list, but you've got a list of different specific heat values for different substances. Okay? Now, if you go down that list, what's the biggest specific heat value by far listed on that page? Water. Okay? So water has a, and this is important, that's going to be liquid water. It isn't ice, it isn't steam, it's liquid water. So the specific heat of water is 4,186 joules per kilogram degrees Celsius. Now, if you did this calculation in chemistry, which I'm guessing some of you did, in chemistry it's 4.186 joules per gram degrees Celsius. So it's the exact same number, but in physics, because we're on the MKS system, we make this kilograms, and so that's why it's a bigger number. Now, to give you some perspective, okay? Let's say that this, I've got a 1 kilogram mass, and just to make the math easy, let's say that the mass of the Earth got a little bit bigger, and G is now 10 meters per second squared instead of 9.8. So we're just going to round it up to 10, okay? So if I take this 1 kilogram mass, and G is 10, it's going to weigh like 10 newtons. And if I take this 10 newton weight, and I lift it up to a height of 1 meter, how much work did I just do? Lifting it from here up to a height of 1 meter.
10 joules.
10 joules, right? 10 newtons times 1 meter, I did 10 joules of work. So I do that so you can kind of see this from a perspective. So if I have a kilogram of water, which is the same as that, to change it 1 degree Celsius, I'm not talking about making it boil, okay? I'm just talking about changing it 1 degree Celsius. If I divide this by 10, I get about 420, okay? So to take a kilogram of water and change it 1 degree Celsius is the same amount of energy involved as me taking this 1 kilogram mass and lifting it up to a height of 1 meter 420 times. So if I sit here and do this, 1, 2, 3, okay? I do that 420 times, I'm going to get tired pretty quick, okay? So, and this is just 1 kilogram, and that's just changing it 1 degree Celsius, okay? I'm not making it boil. I'm changing it from like 20 to 21 degrees or 25 to 26. This isn't big temperature. This is just 1 degree Celsius. Okay. So, obviously, if you look at like copper has a relatively small specific heat, so that means it doesn't take much to change the energy of, or change the temperature of water. Okay, so I got this, we're cool, right? It's just a simple calculation. So, here's what I want to begin to look at. So this mass has to be in kilograms. This change in temperature is typically in Celsius, but it could be in Kelvin, and here's the reason why it doesn't make any difference if it's Celsius or Kelvin, because it's the change in temperature. So, you know, if you go from 20 degrees to 25 degrees Celsius, that's like going from 293 to 298 Kelvin. So if I go from 293 Kelvin to 298 Kelvin, that's 5 degrees. If I go from 20 degrees to 25 degrees Celsius, it's 5 degrees. So it doesn't make any difference which scale that you're working in, because it's the change in temperature, not the temperature. So it doesn't make any difference. Now, mathematically, these are all multiplied together. So if any of these values get bigger, the amount of energy involved is going to get bigger. If I have bigger temperature change, bigger specific heat, bigger mass, because they're all multiplied together, any of those go up, the energy goes up. Any of those go down, the amount of energy goes down. So there's nothing weird like an indirect relationship. There's nothing squared. Okay, it's just a simple, simple calculation. So here's what I want to look at. A lot of times when you talk about energy and substances, you get a graph, a chart that looks like this, where this is temperature and this is energy. Okay, that we're going to dump into the system. So I won't do this because I'm just not. But let's say that I gave, as your lab final, I'm going to give Mary a cube of ice. Okay? That's it. Mary gets a cube of ice. And that cube of ice is at minus 10 degrees Celsius. Okay? That's the temperature of the ice. I bring it out of the freezer. We take the temperature. It's minus 10 degrees Celsius. Okay? And here's Mary's lab final. Is to take that ice at minus 10 degrees and change it into liquid water. Okay, liquid water. That's at 10 degrees Celsius. So she's going to go from minus 10, get it to water at 10 degrees. Okay? So, Mary, what are you going to do?
You can plug it into that equation, the Q equals.
No. I don't want math. Here's your lab final. You've got to take ice that's at minus 10 and warm it up to water at 10 degrees.
You can just leave it out on the counter.
Okay? Why?
Because the temperature in the room is higher than 10 degrees Celsius, so it'll heat up the ice cube.
So it'll heat up, okay? So if this is your ice cube, which direction is the energy flow? From the outside into the ice cube or from the ice cube out into the environment? In, right? That's the direction of the energy flow. Okay? This is why, don't overthink this. Why do you put ice in drinks? Cool it down. So here's your glass of tea, and you put in some ice cubes. Okay? The energy flow is going to go from the tea into the ice cubes. Okay? So the temperature of the water, or the tea, or whatever it is going to drop because it's losing thermal energy into the ice cubes. So the ice cubes are acting as like a thermal energy sponge. Okay? And they're taking this energy in. Okay? So you have to have some source of heat, right? And you're just going to say you're going to let it sit out there and life's going to be good. So what else could Mary do? Besides just letting it sit out. That's kind of boring.
Use a Bunsen burner.
A Bunsen burner. Why a Bunsen burner?
It gives a lot of energy.
So what's going to happen to the time involved if you use a Bunsen
It's
burner?
going to decrease.
Yeah, why?
Because you're putting more energy in the same amount of time.
Yeah, you're going to put more energy in per unit of time. Okay? You can do it in room temperature, but it's going to take a while, right? Put it under a Bunsen burner, wow, okay? Big energy per unit of time. So here's what we're going to do. We're going to start with ice at minus 10 degrees Celsius, okay? And we're going to warm it up eventually up to 10 degrees Celsius. So, and here's what's going to be important, is that that's going to be liquid water, and this is going to be ice. Okay? It's going to be a huge difference between the two. So what's the first thing that has to happen to this ice? What do you have to warm it up to? Can you go straight from negative 10 to 10 without anything in between? Hunter, you shake your head no. Why? Otherwise known as melt the ice, right? Okay? So, it's a keen observation. So, I'm going to start it at minus 10, and I'm going to dump some energy in. Maybe it's from the room, maybe it's from the Bunsen burner, maybe it's from the microwave, maybe you're just holding it in your hands, okay? But I'm going to begin to dump some energy into this, okay? So, at what temperature is that ice going to begin to melt?
0 degrees Celsius.
0 degrees Celsius, right? So here's what I want to look at. I want to calculate how much energy it takes, and let's just make this simple. Let's say that I've got 0.1 kilograms, right? So 100 grams, okay, not a big chunk of ice, 0.1 kilograms, right? You're all familiar with that. Big ice cube, that's all it is basically. So I got 0.1 kilograms, right? And I'm going to warm that up from -10 up to 0. Cool. So anytime you have a temperature change, you're going to use Q equals M delta T C sub P. Right? That's going to be the equation you're going to use. So I've got the mass, no worries there. Okay, that's 0.100 kilograms. Simple. There's my mass. I'm off to the races. Change in temperature. I'm going to go from -10 to 0. So my change in temperature is going to be 10 degrees. Don't make this big. 10 degrees Celsius. Now, here's what you have to watch. On your specific heat calculations, you have 3 different phases of water. You have liquid, you have solid, and you have gas. So you have to pay attention to what phase that water is in. So in this case, because I'm dealing with ice, the specific heat of ice is 2100 joules per kilogram degree Celsius. So my specific heat then is going to be 2100 joules per kilogram degree Celsius. So miracle of miracles, the kilograms cancel out, the degrees Celsius cancel out, I'm left with joules. Life is good, right? So if I do a little bit of mental math, I take 0.1 times 10, I get 1 times 2100, I should get 2100 joules of energy. Now, that energy had to come from someplace. Okay, if you're holding it in your hand, how is your hand going to feel?
Cold.
Cold. Why?
Because the energy is being sucked out of it. Or
Yeah,
it's
that
going
energy
to-
is transferring from your hand into the ice cube. If you put this into a glass of Coke, okay, where's the energy coming from?
the Coke.
From the Coke. Guess what? What's the Coke going to? Why do you put ice in there? Because the Coke is going to feel cold. Okay, right? Because it's giving up that energy into the ice because that's the direction that that energy is going to flow. Okay, put it into a microwave, it's going to be photons, right? Something has to dump that energy into it. Okay. So at this point, I'm at 0 degrees Celsius, and it's still a chunk of ice. So imagine that you've got a thermometer in there, and you're measuring the temperature. So this is where you look at this from like Timmy's perspective, okay? So this is a bunch of room full of second graders, and we have them all, they're so cold that they're held together with little pieces of Velcro, okay? So they've got little bits of Velcro on them. And they're not moving because of the fact that they're all locked in place at -10 degrees. So when I get them to 0, have I increased the kinetic energy of the Timmies?
Yes.
Yeah, because they're a higher temperature, right? That's the nature of temperature. It's a measure of the kinetic energy. So here's what's happening. At this point, I'm increasing the kinetic energy of the ice. So what's happening is that, imagine this. You got a whole bunch of Timmies that were really, really cold, and now they're starting to twitch just a little bit, okay? They're still held together with Velcro. Don't get me wrong, they're still held together. They're still locked in place, okay? Nobody can move, but you can kind of like twitch, okay? All right, but you're locked in place. Okay. Now at this point, we begin to melt ice. So let me give you a quick lesson on ice formation. So first off, what's the chemical formula for water? If you don't know this, I'm just going to lose
H2O.
H2O. Okay?
The only thing I got from Kim one.
And this is a whole hour-long discussion about bond angles and valence electrons and everything else. Because the water molecule looks like this. Okay? Now I hate drawing this because everybody thinks like if you could stare at a water molecule, you can see like a little stick. Okay, and it's held together like, you know, this little H and this little O, and no, okay? These are all electrons going around like this, okay? But here's what's important. Anybody care to guess if the oxygen end is positively charged or negatively charged? Negative. How many valence electrons, quick chemistry review, how many valence electrons does oxygen have?
6,
6. Okay? How many does it want?
8,
8. Where does it get the other 2 electrons?
hydrogen.
Hydrogen.
What
So,
are you looking for?
this oxygen has what we call a dome of negativity, okay? Because it's got some unbound pairs of electrons. Like I said, this is a whole long discussion in AP chemistry. So if this is negatively charged, this end here remains positively charged, okay? So you have like opposite charges. So along comes another water molecule, and so the negative end of this oxygen molecule is attracted to that positive end, and it's just kind of like building with oppositely charged magnets, okay? Positive, negative, but instead of positive, negative, or north and south poles, it's oppositely charged in the molecule. So what happens when you make ice is that you form within this structure something called hydrogen bonds. Hydrogen bonds are very, very strong bonds, and they're so strong that they lock these molecules in place so that they can't move past each other. They can still vibrate, okay? Don't think the electrons aren't moving and all this good stuff. So you have this movement, but they're locked in place, okay? To the point that it's very, very solid. And ice is actually a pretty strong substance, okay? If you ever, this is what allows you to like ice skate, and if you ever try to like chip ice like on a pond or something, ice is pretty hard to crack, okay? Like you can do it, but you have to take like a chainsaw. If you're real aggressive, you take a chainsaw and cut through the ice. Or if you can do a chainsaw and do like ice sculptures and things like that. That's a little bit weird. Okay, but here's my point, is that you've got these water molecules and they're held together very rigidly. So this is like having Timmies, and we're going to hold them in place with this Velcro. We're not going to let them move past each other. We're going to lock them in place, but they can vibrate a little bit. So at this point, we're going to start to dump energy into the system. So we're going to dump more and more energy in the form of photons. Okay, just like light, thermal energy is transferred to photons. So what's going to happen is that these things are going to begin to vibrate enough that we're going to begin to break the bonds that hold the water molecules together as ice. Okay? So this actually goes in 2 different phases. So the first thing that you're going to do is you're going to break the bonds that hold together as ice. It's still going to be a liquid, okay? But it's just not going to be locked in place. So what's going to happen here is that this graph will plateau out for a while. So what this means is that we're dumping energy into the system, but we're not changing the temperature. So that energy has to go somewhere. So what that energy is doing is that it's breaking the bonds that hold the water molecules together as ice. Now, if you look on your equation sheet, okay, on that back side, you're going to see 2 things that involve L. You're going to see LF and you're going to see LV. So LF is what this isn't angular momentum, by the way. So this is called the latent heat of fusion. And this is what's called the latent heat of vaporization. Okay? Cool. Now, which one do you think involves ice and which ones do you think involves boiling water?
Boiling water
Would be what?
LV.
Why?
Vaporization.
It's got the word vapor.
Boiling water has vapor.
Yeah, it's vaping, right?
It's vaping.
Yeah. So, Logan, to continue your thought process. Fusion. So what happens when you fuse stuff together? What do you do? Yeah, which means what?
Great bonds.
Yeah, they're stuck together, right? So latent heat of fusion is going to involve a transition from a solid into a liquid. And latent heat of vaporization, like Grape said, is going to involve liquids and gases, or vapors, depending on. So this can go both ways. So your latent heat of fusion could be one of 2 things. It could either be the amount of energy that you have to remove to make ice. So this is the other thing that I could do to Amy, to Mary. To Mary as her lab final and go, hey, Mary, here's your lab final. I'm going to give you 100 grams of water and you have to turn it into ice. Okay? What would you do? Put it in the deep freeze. What's the function of a deep freeze in terms of energy?
To get energy out.
Yeah, the deep freeze is an energy sponge. Okay? It takes the energy out of the system. So, now it's an interesting philosophical idea. When you put water into the freezer to make ice, it's an interesting concept. Do you add coldness or do you remove heat?
You can't add coldness.
I can't add coldness. Why?
It's just an absence of heat.
Okay? So, the function of, look at your air conditioners on your car. What's the air conditioner? What's the role of any air conditioner? By doing what?
Removing heat.
Putting cold air. Yeah, pulling cold
But-
air in, putting hot air out.
Okay, but what? So how does it make the air cold?
It removes the heat.
It's charged.
Like you plug it in?
Yeah, you have to charge it with I can't think of what it's called.
Well, it used to be Freon.
Yeah, it used to be.
Yeah.
Now it's
So basically, how your air conditioner works is that it removes thermal energy. Okay, that's what it does. So you don't add coolness; you just remove energy. So if I'm going to take water and turn it into ice, I've got to remove energy. If I'm going to boil water, I've got to take water that's liquid and add energy into it and turn it into a gas. If I want to reverse the process and take water that's a vapor and turn it into a liquid, I've got to remove energy. So here's the deal. Y'all seen this probably. It's a hot, humid day. You have a glass of iced tea sitting outside. What happens around that glass?
Sweat.
Starts to sweat. Well, what's the sweat?
It's water that went through the glass.
It's what?
It's water that went
Well,
through
what
the
causes the condensation?
water vapor in the air cooled down
Doing
on the
what?
outside. They're cooling down
Cooling
on the outside
down.
of the glass.
Cooling down and then doing what?
Solidifying more.
Sticky, right? So basically what happens to have condensation on the outside is that you have to slow the water molecules down so that when they run into each other, they're sticky enough to form these bonds. So, and that's going to require energy being absorbed to make these things stick together. So anytime you're forming bonds, water, whatever, you have to remove energy. If you're going to break bonds, you have to dump energy into it. Okay? Universal truth. All right. So if you look at the units, okay, if you look at these numbers, for ice, and this is the one that we're going to use most often, that is 3.33 times 10 to the fifth joules per kilogram. And this is 2 point something. 2.6 times 10 to the fifth. Now, a couple of things about these numbers. First off, you'll note what's different from here that's on the specific heat calculations in terms of units. What's different? There's something on the specific heat units that's not here.
Degrees Celsius.
Degrees Celsius, okay? So why don't you think degrees Celsius is involved here? Don't need it, okay? All this is the amount of energy per kilogram. Change in temperature doesn't matter. And here's the reason why. The reason that there's no degrees Celsius is you go back to this. What's happening here is that I'm dumping energy into the system, okay? Energy is coming in. So because of the fact that I'm melting this, I'm going to go, oh, latent heat of fusion, and this is on your equation sheet, okay? So I got latent heat of fusion is equal to M, then Q is going to equal MLF. So in this case, I've got 0.1 kilograms. And then the latent heat of fusion was 2.33, I think. Times 10 to the 5th joules per kilogram. So here's what's important. Conceptually, this is what you have to understand. Is that in this situation, I'm dumping energy into this ice, but I'm not changing the temperature. Okay, listen to me. I am not changing the temperature. What that energy is doing is that it's breaking the bonds that hold the water molecules together so it can exist as a liquid. So this is a situation where energy goes in, but I don't change the temperature. So I'm not changing the kinetic energy of the particles. I'm breaking the bonds that hold them together. So if I take 0.1 times this, I get, trust me on this one, 3.33, is it 3 threes? 3 threes.
Yeah.
0, 0 joules. So here's the difference. Just to warm up the water from negative 10 to 0 only took 2100 joules. Okay? It's not a whole lot. To break the bonds and turn it in from ice into liquid takes 33,300 joules. Now, if you look at that, that's just for one ice cube. Okay? That's just for one ice cube. This is the energy that it takes for one ice cube, 100-gram ice cube. So everybody says, well, you know, oh, the ice caps are melting. Well, imagine how much energy it takes to melt a glacier. Okay? Yeah, it's a tremendous now. But here's the potential like downward cycle. So you've got this energy that we're excess energy in the atmosphere, and you're going and it's absorbing because of the fact that we're melting glaciers. Well, worst case scenario, the glaciers all melt. That's a worst case scenario. Now you've lost a big chunk of ice that's capable of absorbing energy. And now that energy, instead of being absorbed to melt ice, is going, oh, now what do we do? Oh, let's warm up the ocean. Oh, that's cool. No. Okay. Oh.
Iceberg epidemic right there.
So we need to make fake ice.
We need to make fake ice.
How exactly?
Just throw some styrofoam in the ocean.
Yeah,
Take care of it.
yes,
Just
Put air conditioners.
It looks like ice from a distance, so it'll
Yeah,
fix
and
the
it floats.
problem. Yeah,
We can
Ozone in there.
stuff.
we'll confuse science.
Okay.
And also,
All right.
styrofoam doesn't melt.
So
Yeah, just
here's
air
what's
conditioning.
happened.
I don't honestly
We
just
took
start
ice
throwing
at
ice in
minus
the ocean.
10, we warmed it up to 0, and then we've melted it. So at
That's what I
this
do.
point, it's water. Okay? Now, that's kind of cool. So here's what I want you to think about. So on your phase, you have this ice cube, right? We added all of this energy to it, and then it turns into this little like puddle of water. Okay? Right? So when you look at what has to happen, we broke the bonds that held it together as ice, but they're still held together enough to exist as a liquid. Now, think about this, and assuming the bodily fluids are mostly liquid, or mostly water, which they are. In your day-to-day experiences, other than water-based stuff, okay, whether that's blood, pop, whatever, okay, what other liquids do you consistently run into on a daily basis?
Liquid iron.
Or we're just talking like generically, or?
Yeah, I mean, seriously, other than water-based substances,
Gas.
what, okay, you got gasoline, okay,
Mineral oil.
huh,
Mineral oil.
mineral oil,
Corn syrup.
yeah, corn syrup, or just syrup in general,
Syrup in
maple,
general.
Yeah.
Maple?
High
Yeah, maple
fructose
syrup,
corn
yeah.
syrup.
okay, Aunt Jemima, whatever,
Honey.
Aunt Jemima, that's the move.
okay, honey,
Yeah.
Ooh, honey's so
but on a regular basis, though, those are kind of special needs situations, right?
Yeah.
Okay?
Yeah.
All right, unless you're McGriddle, and then, okay, then you're all over the, you know, okay? But, so, in what form are most of the stuff that you encounter?
Water-based.
No. Solid, liquid, gas. Most of the stuff that you
Solid.
encounter is what?
Oh,
Solids. Yeah, you encounter some gaseous phases every day?
Yeah.
Yeah, it's this atmosphere, right? It's kind of cool that we have it.
What do you
Okay?
mean though, like?
a lot of gas.
Like, what do you mean? What was the question? Like, what is the most?
So here's my question. If you look at the most of the stuff that you encounter, it's solid. Your clothes, the table, your pencil, your car,
More like
glass.
air, like more gases. 'Cause, like that's what I was trying to say.
The entire Earth is.
Yeah. I know, but we don't
Earth
just
is
made up.
Of course we do. We got you. Yeah, we do have this thin layer of air which is around us, which is a cool thing.
Yeah.
Okay, don't get me wrong, right? But I'm just trying to get you to think that you realize most of the substances you encounter aren't liquids. They're either gases or they're mostly solids. So here's the odd thing about liquids, is that they're in a balancing act. They're still the particles are still held together, but they're loosely held enough that they can flow past each other. Okay? Now, you look at butter. You let butter sit out for long enough time, what does it become?
Liquid butter.
Liquids. Okay, so you're basically like, I knew that would get Legretto excited.
Man,
Well, no, look at him. Man. You cannot look at that man and tell me that that man does not look like a good piece of melted butter on top of his pancake. Am I wrong?
Oh my God.
Am I wrong?
that one hurt a little bit.
No, it did not. I'm right, aren't I? Am I right?
Sure.
Okay. Okay.
Did anyone eat pancakes without butter though?
He's talking about your arms.
You eat pancakes without butter?
Yeah, it's called healthy.
You're a weirdo, so it makes
It's
sense.
called healthy.
You guys are all liars.
Now, what I do is put a fried egg.
You put margin on it?
No. I put a fried egg on top of my pancakes. And
That
then,
sounds
And you don't like McGriddles.
I know.
What?
Do you like the muffins?
Anyway, here we go. Okay.
Dude,
So-
the pancake up.
I stopped myself.
Okay, so in the name of time, so here's what we've got. We've got water, we've got 100 grams of it, right? So now I need to take water that's 0 degrees Celsius and warm that up to 10 degrees Celsius. So anytime you have a temperature change, now we're going to go back to Q equals M delta T C sub P. I've still got the same mass, right? Which is 0.100 kilograms. Now I'm going to go from 0 up to 10. I've still got 10 degrees. But now I'm going to use the specific heat of water, which is 4,186 joules per kilogram degree Celsius. Miracles cancels out. I get 4,186 joules. That's crazy. So here's what I want you to look at. Is that to take ice that was at minus 10 and warm it up, that took 2,100 joules of energy. It's going to take 33,300 joules of energy to melt the ice, okay? And then to make that transition from 0 degrees as a liquid to 10 degrees as a liquid, that's going to take 4,186 joules. So if I added all those together, that would be the total amount of energy it would take to take ice at minus 10, melt it, and then warm up the water. Now,
No.
what?
We're gonna have charts again?
No.
Okay, good.
No. Chill, man.
Don't worry there.
Okay. Chill, man. No. Now, if we really wanted to make it difficult for her, because I think she's up for the challenge, we take ice at minus 10, we warm it up, we melt it, and then we make it boil. So what temperature does water boil? 30 degrees Celsius. How about 100 degrees Celsius, right? So now, once I hit 100 degrees, what's this line going to do? It's going to plateau out because now I'm dumping energy in to break the bonds that hold the water molecules together, otherwise known as creating vapor. Then, if I really wanted to, then I can warm up the steam. Okay? Now, so this is how we typically generate electricity. So this is why it's so inefficient to generate electricity like we do, why it wastes so much water. So basically what happens at most electrical facilities, you take a huge vat of water and you boil it, which takes a tremendous amount of energy because you got to boil water. Then you take the steam and then you add more energy to the steam. So then you heat up the steam. Oh, okay. So now you have steam with all this kinetic energy. Then it hits a turbine, okay, and it makes the turbine spin. Okay? So now this thing is spinning. Then that's hooked up to a rotor, to generate electricity, we can make toast. But here's the problem.
You love toast.
With butter.
It's horribly inefficient because of the fact that you've got to heat up the water, heat up the steam, and then do this. So the beauty of solar panels is they sit out there.
It's advertising.
No, I'm just saying. Photon comes in here, hits it, boom, we get electricity. You don't have the water phase. So as water becomes more and more critical as a resource, this is the other advantage of solar, is that you're not wasting all of that water. So like our solar system will save about 60,000 gallons of water a year. So because of the fact that you don't have all of that wasted stuff. So it's a good news, bad news day. No, you don't have any homework. So
That needs to go viral on YouTube.
Yeah. Landon, stop.
No homework,
Landon.
You can't